Assalamu alaikum everyone. So welcome to the second lecture in the O-Levels-IGCSE physics series. Today's topic will be kinematics. But before I talk about that, just a little bit about what the MUS Initiative is. So the MUS Initiative is an initiative designed to help students all around the world in subjects like mathematics, physics, and so on and so forth, like up to the first or second year college courses. And basically the whole purpose is to explain and clarify core concepts in these areas in a very simple manner, all right, and an interesting way. The motto that we go by is learn, earn, and give. So basically, you learn to earn, and then you earn to give. And I strongly believe, that giving is more. So last time we talked about physical quantities, units, and measurements, which was in a topic in general physics. Today we will start with Newtonian mechanics. And the first topic will be kinematics, the one that we're going to cover in this lecture. So kinematics is basically, the study of physical quantities that describes the motion of the object. Now, we see things in motion all around us, right? So kinematics is the branch that deals with describing that motion. So in the learning outcomes for this topic, the last two, I highlighted them in red. The reason being that I thought it would be better to talk about these when we cover forces, balanced and unbalanced forces in dynamics, and that's when it will be much better to introduce these these subtopics. And the other thing that I want to clarify is that in this physics series, we will only deal with one-dimensional motion. What do I mean by that? That you can only travel in a line. If you draw a line, in this case, it's a vertical line, you can only travel either up or down. If it were a horizontal line like this, you could either travel left or right. So we're dealing with one-dimensional motion here. All right. So, last time we talked about base units, right? There are three fundamental units that we have, and they are mass, which we measure in kgs, length, which we measure in meters, and time, that we measure in seconds. Now, before talking about the motion, right, we need to describe two very basic quantities, distance and displacement. Now, one of them is a scalar and the other is a vector. So the distance is the scalar quantity, right? It only has a magnitude, right? And displacement, on the other hand, is a vector quantity, which means it has a magnitude and a direction. All right. So scalars, they can only take, positive values. For vectors, because you can go in both directions, if one direction is positive, the other has to be negative. Now, the whole idea is, let's say there is this point A and point B. And let's draw another point C. Now, I measured the length between A and B. And let's say the length between A and B is equal to 20 meters, and the length between A and C is equal to 10 meters. Now, let's say I take a very weird type of path. I walk from A all the way to B. If I ask you what the distance is between A and B, given that I followed this path, I would have to measure the length of this entire path to give that answer. That will be my distance, right? And I don't know what that is right now because I took this weird looking path, right? But that would be my distance. But if I ask you what is the displacement is basically the shortest linear path from the starting point to the final point. So let's say I started from A and I went to B. And so my displacement would be 20 meters. All right. Now let's say I ask you what the displacement from A to C is, like at point C. Like if you're at point C, if I go from point A to point C, right? what's my displacement going to be? Well, it's going to be negative 10 meters. Why negative? Because if the origin, let's say this was my origin, and if I'm traveling to the right, then it has to be positive, if I consider that positive. If that is positive, then to the left, we're going to have a negative displacement. All right. Okay. So given this, now I have a question, a quiz. Let's say I have point A, and I go in a circle, and I come back to point A. And the radius of this circle is 2 meters. What is the distance that I traveled, and what is the displacement? So the distance is basically the entire path, the length of the entire path that I traveled. Now we know that the circumference of a circle is 2 pi r, right? So we can just plug in r equals to 2. And so we'll have 4 pi, let's say it was all in meters, right? So 4 pi meters. But what about the displacement? Since the starting point and the final point is the same, right? So the displacement is 0. There is no displacement. All right. Okay. So the three distances are that we need to know about. They're just minor details. Is the thinking distance, braking distance, and stopping distance. Well, let's say I'm traveling on the road and I see an accident at this point. So I'm traveling on a car, and when I travel at point A, I see that there is an accident. So before that, I did not know. At point A, I saw the accident. Well, when I saw it, I reacted to it. But there is this short time interval in between, right? Before me seeing something and then acting on it. So at point B, I acted on what I saw by applying my brakes. And then at point C, just before the accident, thank God, I stopped, right? So the thinking distance is basically the distance between when I saw something and I acted on it. The braking distance is when I acted and I finally came to a halt. And the stopping distance is the entire length. All right. So moving on. Now that we've talked about, distance and displacement, how can we use this to describe something that's very meaningful? Let me give you an example. Let's say that from A to B, there's this short path from A to B, and I see that there's this guy, let's call him person A, who walks from A to B, all right, or runs or jogs or whatever. And the same route, I'm just going to draw it on a separate, I'm going to draw it separately because I don't want to overlap. I have person B. Let's call this person 1, and let's call this guy, oops, my apologies. Let's call this guy person 2. Now what I notice is, that from A to B, person 1 walks, covers the distance much faster than person 2. It took more time for person 2, he covered the distance more slowly, right? So is there some quantity that I can define that measures this, right? Like how fast someone covers a specific distance, right? And the answer is yes. And the quantity that measures that is speed or velocity. Now again, the difference is that speed is a scalar and velocity is a vector. So, what I do is, person 1, his speed, let's call it average speed, is, first of all, the formula for speed is distance divided by the time taken. All right. So basically it makes sense, right? Like how much distance are you covering in a given time? So let's say that the distance is the same in this case, right? In this case, A to B. But if person 1 takes less time, then it means that he walked faster, right? Let's say the distance was 10, right? Let's say the distance was 10. So person A took 5 seconds to cover that distance. So his speed was 2 meters per second. Let's say it's all in meters. But person B, on the other hand, took 10 seconds So his speed was 1 meter per second, right? So basically, you know, when we write this formula, so distance divided by time, into a more mathematical form, what we would say is, you know, d2 minus d1 divided by t2 minus t1. So d2 is the time, is the distance at B, all right? This is d2. And d1 is from where I started, so it was point A, all right? And t2 and t1 are the time measurements that I made at point B and at point A. So t2 was at point B, and then t1 was at point A, all right? So we can say that d2 minus d1, this guy right here, can be called, you know, the change. It can be thought of as the change in distance, right? And similarly, t2 minus t1 would be like the change in time, right? So if we have something that's changing, you know, that's changing over something else that's changing, is there another way that we can, you know, that we can refer to it as? And the answer is yes. We can call this as this guy, d2 minus d1 divided by t2 minus t1, which can be written as, in short, as delta d divided by delta t. All right, the change in distance divided by change in time. Well, this whole thing can also be thought of as the rate of change of d with respect to time, right? With respect to time. So d in this case is distance. All right. Okay. So this is how we measure speed. Like, speed tells us how much distance you cover in a specific, how quickly you're covering some distance. Then what is instantaneous speed? Well, let's think about this, right? At point B, the next measurement that I made, let's say now I'm only looking at person 1, right? This guy right here. So I make the time measurements at the distance and time measurements at point A and point B. So that's all I know. The measurements that I make at 2 specific points. At point A, I had, let's say, d1 equals to 0, and then t1 equals to 0. And then at point B, I had d2 equals to 10, and let's say, you know, t2 equals to 10. All right. So those are the measurements that I only know of. So based on these measurements, I can measure the speed, which is, you know, 10 minus 0 divided by t2 minus t1, which is 10 divided by 10, equaling 1. All right. But is this the true speed though? Well, think about this. If the person, before reaching point B, if in the center somewhere, I don't know that because I'm only concerned with the measurements that I made. I didn't see him all the way, like I didn't see him walking all the way from A to B. I just saw him at point A and then I saw him at point B. If during the journey, if he stops for, let's say, 2 seconds or 3 seconds, let's say at time t equals to 1 to time t equals to 5, he stopped. Right? And then he continued his journey from time equals to 5 seconds, t equals to 5 seconds, and then reached point B at t equals to 10 seconds, t2 equals to 10 seconds. So, I mean, I would still measure the velocity by using points A and B because those are the only measurements that I know of. But this is not the true measurement, right? Because at time t equals to 1 second, the guy stopped. And then 5 seconds, he started moving again. So what is instantaneous speed? That's where instantaneous speed comes in. The whole thing is that I want to take, let me draw it here again, A and B. The whole thing is that the person was at point A. So to get more close to the true value of what his speed was, let's say this was d1 equals to 0 and t1 equals to 0. What I'm going to do is I'm going to make another measurement, but I'm going to decrease my time interval. Like I'm going to make a measurement very quickly after time t1 equals to 0. Let's say at time t1 equals to 1 second. I'm going to measure the distance. Let's say he covered 0.5, right? So now the value of speed changes, right? It becomes 0.5 divided by 1, which is 0.5 meters per second. The whole idea of instantaneous speed is to take the second time measurement, my apologies, this should have been a 2, to take the second time measurement as close as I can to the first time measurement. The closer the time gap is, the truer the value I know of what the speed is going to be. All right. So that's where instantaneous speed comes into play. Like what's the speed in that instant, like right after 0 or right after some other time point, right? Like for example, if I wanted to know the instantaneous speed at time t1 equals to 2 seconds, I would make time 2 very close to t1, that's say 2.0001 seconds, right? To get the instantaneous speed. The velocity is, basically, it's just speed, but with a direction. So let's say if the person is walking to the right, then we will consider that as a positive velocity, all right? And if you were moving to the left, we would call that negative velocity. All right, so the speed is going to be the same. Let's say the speed to the right was 2 meters per second. The speed to the left was also 2 meters per second, like the speed at which he was walking. But the velocity, right, is negative because he was walking in the opposite direction. Okay, so I hope that makes sense. All right, so moving on, I have a small quiz. So, A0 is this point right here. Now, all I want you to do is just tell me what the velocity and what the sign for the velocity, like is it going to be positive or negative for the velocity and the displacement at, let's say, points 1, 2, 3, and 4. All right, did you get it? So if you look at point 1, for example, since point 1 lies to the left of A, and just for your reference, to the right, the velocity is going to be positive. All right, velocity is positive, and we're going to consider displacement positive as well, to the right. All right, positive. All right, so at point 1 lies to the left of A. So if everything to the right of A is positive displacement, then everything to the left should be negative displacement, right? So the displacement is negative. What about the velocity? Well, moving to the right is positive, so I'll say this is positive velocity, but negative displacement. What about point 2? Well, point 2 is, again, lies to the left of A, so it's negative displacement. But what about the velocity? Well, the velocity is going to be negative, because if moving to the right is positive, then moving to the left is negative. For point 3, you're moving to the right, so velocity is positive, but the displacement is positive as well, because now it's to the right of A, and everything to the right is positive displacement. What about 4? Well, 4 is negative velocity, but positive displacement. All right. Now, a quick quiz. Let's say this is point A, point B, and point C. And the distance between points A and B is 10. And the distance between points A and C is also 10. Now, I go from A to B to C. I want you to tell me what the distance traveled is going to be and what the displacement is going to be. All right, so the distance traveled is, first I go from A to B, and I go from B to C. So I went, from A, I covered the distance A to B, which is 10. Then when I was going back to C, I covered another 10 because I had to go from B to A. And then I covered, from A to C, I covered another 10. So that gives me 30 meters, if the distances are in meters. What about the displacement? Well, the displacement is just the shortest path between the starting point and the ending point. So the starting point was A, the ending point was C. So, it's just the displacement is just, the shortest distance between those 2 points. So that's 10, right? 10 meters. But because it's to the left, it's point C, I'm standing to the left of A, which is my starting point, it's negative 10. All right, so I hope that's clarified. Let's move on. Gradients. Now, before we start talking about, distance, displacement time graphs and speed and velocity time graphs, the concept of gradients is very important. So the simplest case is as follows. Let's say I have this y-axis and x-axis. Usually on the x-axis we have time, we have independent quantities like time, which is independent. It doesn't wait for anyone. It just keeps on moving forward. And y is something that we're measuring with respect to time. It can be distance, it can be velocity, or whatever. All right. So the simplest case is a straight line. You know, the equation for this is y equals to mx plus c. So there are two things to consider here, right? The first is m, and the second one's c. What's m? M is basically the slope of this guy. How do you measure slopes? Let's say I had points 1 and 2. Well, I take the coordinates and I'll subtract them. Let's say, so it's going to be y2. How much did y change when x changed between points 2 and 1? So that's my slope. And what's c? Well, if you plug in x equals to 0, right, which is x is going to be 0 along this axis, right? X has a value of 0. So on this axis, on the y-axis, only y changes, but x is 0. So what about c then? Well, if I plug in x equals to 0, I get y equals to c. Well, this tells me something. This tells me that c is basically the starting value of y. Basically the value of y when x equals to 0. X can be time and y can be distance. So the distance at time t equals to 0. All right. So these two, like the gradient and the intercept, are important to know, like the idea behind them. All right. So for a linear graph, let me draw it once more over here. Let's say this is a linear graph. Now, I told you what the gradient is, right? The gradient stays constant. Now, what do I mean by that? Let's take point 1 and point 2. Let's call this time and let's call this distance. All right. So between 1 and 2 seconds, and let me take point 3, point 4, and so on. So between 0 seconds to 1 second, let me just label these points as well. 1, 2, 3, 4. Between 0 to 1 seconds, I can see that when I went forward in time by 1 second, I moved a distance of 1 meters, right, on the y-axis. All right. If I go, so the gradient is what? The gradient is going to be, 1 minus 0 divided by 1 minus 0, which is just 1. What about the gradient after this point? Well, I mean, you can take the next interval, the same time interval of 1 second. All right, not 2 seconds, just 1 second. You can take 2 seconds as well, it's up to you. But let's just take the next time interval of 1 second. So I move another 1 second. And I measure what the distance at that point is going to be at 2 seconds. And it's 2, right? So I can say the gradient then is, 2 minus 1, because at 1 second my distance was 1, divided by 2, which is the time, 2 seconds minus 1 seconds. So I again get 1. So the good thing is that, this gradient is uniform. All right, it's constant. It's constantly changing. Why? Because you cover equal distances in y, in this case t, in equal intervals, time intervals, or equal intervals of x. Okay, so that's the first fundamental case. All right, case 1. Let's move to case 2. Well, let's take this guy for an example. We see that something is increasing, right? So I again do the same thing. All right, but this I'm not going to write down the numbers. I'm just going to explain it. Let's say this is 0.1 for me. Then I have 0.2, 0.3, 0.4. They're equally spaced. And I measure that if I go from 0.1 to 0.2, what's the change in this quantity on the y-axis? And the change is this much, right? This guy right there. But if I go from 2 to 3, let's say another by the same amount, if I go forward, what's the change between 3 and 2? Well, it's this guy. All right. All right. What if I go from 3 to 4? Again, I measure. So I can see that basically, you know, the change in y is increasing as I go to the right. Right? The change in y is increasing as I go to the right. So in this case, I'm going to say that, you know, m, which is the gradient, I mean, the gradient is increasing. Why? Because just think about it this way. You know, between 1 and 2, I can treat points 1 and 2 like a straight line. And then between 2 and 3, I can treat 2 and 3 like a straight line. And 3 and 4, I can treat that as a straight line, right? So all these straight lines, when they add up, they make like a curved shape, right? But in that very interval that I consider, 1 to 2 or 2 to 3, that's when I only consider that as a line, right? I can see that the gradient is getting more steep, right? So the gradient is increasing as I go to the right. So that we will call this an increasing gradient. So say something's increasing. All right. And the final case that we're going to consider is case number 3, which is something like this. All right. Again, the same thing. Let's define, you know, let's take this 0.1, 0.2, 0.3, equally spaced. If I look at the change in the y-axis from 0.1 to 0.2, it's this much. If I look at the change by going another, by the same amount in x, if I go from 2 to 3, I can see that the change has reduced. And so you can see that, you know, the change in y is decreasing with equal changes in x. So if the change in y, you know, y2 minus y1 or y3 minus y2, whatever, we have x2 minus 1. So this guy is the same, right? This is not changing. But this guy is decreasing as I move to the right. And so this is a decreasing gradient, right? Basically the gradient is decreasing. And in case number 2, the gradient was increasing. Now, these were positive gradients, right? Now, in the very first part, when I was talking about when I drew this, I just drew a positive gradient. Well, we can also have negative gradients. Negative gradients are just the opposite. All right. Why? So let's say, you know, this was 0.2 and this was 0.1. I'm basically from the top, I'm coming to the bottom. And so you can see that, you know, it's going to be y2 minus y1 divided by x2 minus x1. Well, you know, x2 minus x1 is going to be positive. Let's say, you know, this was 0.2 and this was 0.1. But if you look at y2 minus y1, y2 is lower than y1, right? This value is much lower than this value. So this is going to be negative, all right? The gradient is going to be negative. And so the other way I could have drawn cases number 1, 2, and 3 is as follows. I could have drawn it this way. In this case, again, I should have said this, the gradient is increasing uniformly for case number 1. When I was initially doing this, not just uniform, increasing uniformly. So what about this guy right here? Well, it's decreasing uniformly. All right. With case 2, I can draw something like this. Right? It's the exact mirror image if you reflect it across the x-axis. This is decreasing gradient, basically decreasing let's say decreasing gradient. But basically, you know, the gradient is becoming I shouldn't have said decreasing gradient. Let's say it's becoming more and more negative. So it's increasingly becoming negative. So increasingly negative gradient. And for the third case, it's going to be something like this. So this is basically a decreasing negative gradient, right? So this is very important when we talk about distance time and displacement time graphs. So let's move on. All right. This question, we haven't talked about forces yet. We haven't talked about friction. We have talked about speed though. But the whole idea of this question is to basically, tell you how to answer MCQs in case you don't know something in the answer choices, and you have different options that you have to consider. So basically, we have talked about braking forces. So so a student lists three changes that affect the stopping distance of a car, and we want to tell that which change or changes increase the stopping distance, right? So we haven't talked about forces. So for a moment, even if you know about forces, let's just put a question mark there. I mean, I am not sure if one is the correct answer. What about two? Well, increasing the friction between the tires and the road. Well, I mean, even though I don't know about friction, but there's like, I don't know friction as a force, but I do know that friction is something that, is opposing me, or something that's stopping me. There's friction. There's friction in our friendship or whatever, just as an example, like something that's stopping me from moving on. And so, I'm like, okay, if I increase the friction between the tires and the road, well, it's going to stop me more, right? So it's going to decrease the stopping distance and not increase it, right? So I can check, I can cross off the second choice, because I know that that's not true. Increasing the friction would decrease the stopping distance, right? What about increasing the speed of the car? Well, if I increase the speed of the car, I need more. I'm going to be covering more distance, right? I need more time to stop. And if I need more time to stop, I travel more distance. So 3 is correct. At this point, we know that 2 is not the right choice. So we can cancel the answer choices, get rid of the answer choices that have 2. So we get rid of 2. And the other thing that we know is that 3 has to be an answer. So I can cancel, get rid of the option C. All right. Now it's a 50-50. Now at this point, the first step would be to use intuition. And if intuition fails, then just, pick one. All right. So let's use intuition. Increasing the braking force. Well, I've heard about forces, like in general conversations. Like I don't know what the physical context of this is, but like it does make sense. Like I'm increasing the braking force. So if I'm increasing the braking something, then I need to be stopping quickly, right? So it will decrease the stopping distance. So now I know that one has to be when one's wrong. So I cancel, get rid of option B, and I choose D. But even if you didn't know about one, let's say, then it's just a 50-50. Pick B or D. All right. So let's move on to distance time graphs. Before we talk about the gradients and everything, there are 3 things that we have to know. First, it tells us how the speed of the object is changing. It can tell us what the velocity will be till a certain point. After which we cannot know anymore if the velocity is positive or negative. But it does tell us about velocity to a certain extent, and we will talk about that. And the third point is that the gradient is what tells the velocity. So all right, so how to visualize? Let's say I have this point with time here, and this is my distance. Now I draw something like this, how the distance changes with time, and so I ask, before delving into figuring out what's happening, let's just try to visualize. We introduced time, and that's why the graph looks like this, right? You cannot see time, right? If something is moving, let's say up and down like this, right? I'm moving in time, right? Right now we're all moving through time. But for us, it's just moving up or down. But we want to plot this with respect to time. And so when we plot it with respect to time, right, I make all these time measurements, like, I'm going up and down, but like at t equals to 0, I was here, 0.1, I was here, 0.2, I was here, 0.3, I was here. And that's what the graph looks like, looks something like this. So the better way to visualize this is like, think of the particle on the y-axis over here. Now as time goes on, it's traveling to the top, all right, upwards. And at this point, right, till some certain point, let's say this was T1 and this is T2. So by t1 seconds, it got to this point. So it moving up, got here. From t1 to t2, it just stayed there. All right. And then from t2 onwards, it just came back to 0. All right. So that's a good way to visualize, these distance time graphs. Now I can also draw it on the horizontal scale. So basically, I was initially here at time t1, I was traveling, let's say, I translate the motion. So I'm taking the down to up motion from left to right. So I got here at time t1, this was time t0. And at time t1, I stayed at this place from t1 to t2. And then I finally moved back and came back to the distance of 0, where I started, given that this was my origin, all right? This point right here. Okay. So let's look at a uniform velocity displacement type graph to keep things simple. So I'll draw this graph right here. And something like this. All right. Let's call this T1. Let's call this T2. This is time. This is distance. All right. So, I ask the following questions. Basically, let's call this T3 and T0. So between T0 to T1, then T1 to T2, T2 to T3, I want you to tell me what the speed is and what the velocity is. All right. Just explain if like the speed's increasing, constantly increasing, it's 0, constantly decreasing, that sort of thing. Just that. All right. So let's just look at speed first. So from T0 to T1, we see that the gradient's constant. So the speed is, constantly increasing. Then from T1 to T2, well, look at this. So we move up. And then from T2 to T3, T1 to T2, it just stays there. So the speed is 0. And then from T2 to T3, it starts moving down. And so it's constantly increasing again. Now, see, I did not say constantly decreasing. Why? Because remember, look at the motion. Within the motion, the speed does not care about directions, right? It just talks about it's just the magnitude. It's just the way I'm moving, right? It has nothing to do with direction. It doesn't matter if I'm moving up. It doesn't matter if I'm moving down, right? The speed is increasing, right? I went from point T0 to T1 and I had some speed that to cover that distance, and I stayed there, and then I went from point T2 to T3, right? And again, from point T2 to T3, the speed had to increase because I was at a stop from T1 to T2. So from T2 to T3, it constantly increases again. Now, what about velocity? Well, velocity, the direction matters, remember? So from T0 to T1, when I'm moving up, let's say moving up, I'll consider that as positive. So, it's constantly increasing. All right. From T1 to T2, it's again 0 because, the particle's at a stop, so it doesn't matter what the velocity is. I mean, if it's stop, it has no direction, and so it's 0. But then from T2 to T3, it starts moving down. So when it starts to move down, it's constantly decreasing because the direction's opposite. So the speed's the same, right? The speed doesn't, like, the speed is always going to be positive, but the velocity is going to be positive when the gradient is positive. You can see that this is a positive gradient and this is a negative gradient. And so the direction of the gradient tells us if a vector, in this case velocity, is positive or negative. But the speed only cares about the magnitude, like the way the gradient's changing, like the steepness, in other words. So the speed only looks at the steepness. It doesn't look at the direction. All right. Okay, I hope that's clarified. So remember I said that the distance time graph, first of all, distance can always be positive. Why? Again, because it's a scalar, so it can be 0 or positive, but it can't be negative. It doesn't have directions to take account of. So what if, let me just take this graph right here and extend it a little bit. So this was T3. Let's say I make it go up like this again, and I'll call this T4. Well, now what happens? Here's the tricky part, right? Here's where the distance time graph will stop telling us about the direction of velocity. So from T3 to T4, one thing's for sure, the gradient is increasing, right? So, I mean, it's going up. I mean, it doesn't matter if it's the gradient's like positive or negative. The speed has to increase, but it's what we have to look for. Is it constant? Yes. So it's constantly increasing. But what about velocity? Well, think about it this way. I'm going to translate the motion, this upward and downward motion, to a right-left motion to make it much easier to understand. Let's say at time t0, I was at this point. So moving up was positive. In this case, I'm going to say the translated motion, moving to the right is positive. So from t0, at point t1, I'm moving to the right at t0. And at point t1, I reach this point. At t1 seconds, I reach this point right here. Okay. So we know that the velocity is positive. Well, then from t1 to t2, I stay at this point. So the velocity has to be 0 because it's just staying at this point, right? Okay, then from t2 to t3, I see that, the particle, look at this, so it goes up, and then from t2 to t3, it's going down. So down is going to be left in this case. So it's going to, at t2 seconds, it starts moving to the left again. And it reaches the origin, where you can see at t3, the distance is basically 0. So I'm at the origin again. So at t3, I'll just put t3 down here. I'm again at the starting point, right? So my velocity when I started at t2 seconds till t3 was, because I was moving to the left, my velocity was negative. See, it was constantly decreasing. But what happens after t3 seconds? Well, after t3 seconds, do not get confused. Why? Because there are two cases. Let's say I'm at this point now, right? If I move to the left a certain distance, let's say, or if I move to the right a certain distance, right? Either this way or this way. Both ways, my distance is going to be positive, right? Because distance can't be negative. If I measure the distance here, that's going to be positive. If I measure the distance here, that's going to be positive. So the distance is never negative. So what this graph shows me is that once I go up and down, or in this case, when I go right and left and come back to the origin, right? If then this distance starts to increase, which it does, at t3 starts going up, the distance increases. I'm not sure if it is moving to the right or to the left, because in both cases, the distance is going to increase. All right. So at this point, we do not know if the velocity is increasing or decreasing, because if it were to move this way, it would be positive. If it were to move this way, it would be negative. But what we do know is that it will be either constantly decreasing or constantly increasing. All right. Okay. Now there might be, a confusion, a small confusion. Let me clarify that. And the confusion is that, let's say, this is point A and this is point B, and I was going from point A to point B, and then I came back from point B to point A. Well, the displacement is definitely going to be 0, right? But what about distance? Well, if I ask you what's the total distance covered, and let's say, this distance, the length that I measured between A and B was 10 meters, the distance, the total distance would be 10 plus 10, which is 20. But if I ask you that, you know, you went to B and then came back to A. I just want to know your distance at point A. Well, you know, my distance at point A is, you know, just 0. If I'm just asking for a distance at that point, right? If I asked you for the total distance, that would be, 20. But if I ask you for like just the distance, you know, not the total distance, not the distance traveled throughout, but just the distance at point A, that I can measure with respect to, you know, the starting point. Well, you know, it's going to be 0 because I am at the starting point, so there is no distance at that specific point. In other words, you know, but it's shouldn't be confusing. The displacement has to be 0, but distance at specific points versus the total distance traveled is something different. All right. Okay. So let's look at this question. A train sets off from a station at time t equals to 0. The graph shows how the distance between the train and the station varies with time. Which statement about the movement of the train between time t1 and t2 is correct? Now, we know that the distance time graph, the gradient of the distance time graph, it tells us what the velocity, it tells us what the speed is. It can tell us about the velocity, but usually we shouldn't be talking about velocities when we look at distance time graphs. All right, so the speed, let's look at this point, right? So it's not, so it's increasing the distance, you know, as we move on in time, it's increasing. So it's going away from the station. So the station was at point 0. So we're going away from the station. And then once we reach point, t1 seconds, we start going back. And at this point, for a short time at t1 seconds, the particle stopped, right? It wasn't moving. But then immediately after t1 seconds, like really, like a very tiny time interval after, I see that the distance starts to change again. And so it starts moving down. So if I'm just talking about the speed is increasing, right? It can't decrease. The speed is increasing. Okay. And is it moving away from the station or is it moving towards the station? Well, I mean, just look at this. The station is at point 0. So when I was going up, I was moving away from the station. But if I'm going back down, I'm moving towards the station. So the answer choice is D. All right. Displacement time graphs. Well, it's pretty much the same thing, just with a slight twist, and I'll mention that. Basically, it tells us how the velocity is changing. It does tell us about the speed because, you know, we'll talk about it when I draw the displacement time graph. And the gradient is what tells the velocity. Now, let's not the gradient this time with its steepness and the direction is what tells us the velocity. All right. But the speed is only about the steepness of the gradient. Now let's look at uniform velocity displacement time graph. So let me draw a graph, the graph again. I'm going to draw the same graph that I drew previously. T0, T1, T2, and T3. Well, the same thing, you know, like I'm going up, and I'm going to stay there, come down, right? And then I'm at this point. Well, when we were, you know, talking about what happened between T0 to T1 and, you know, so on and so forth, we were talking about, you know, speed and velocity. Well, even if I look at this displacement time graph, right? Displacement. Even if I look at this displacement time graph, I see from T0 to T1, the speed is increasing, right? I only have to look at the gradient constantly increasing or uniformly increasing. What about the velocity? Well, the velocity is positive. Why? So it's constantly increasing, right? It's positive, constantly, or in other words, I can say constantly increasing. All right. What about T1 to T2? Well, I mean, we talked about this earlier. The particle stopped, so, you know, both are 0. What about T2 to T3? Well, you know, I'm just looking at the gradient for speed. So the speed is again increasing constantly because I'm only looking at the gradient, the steepness of the gradient. But with velocity, because the gradient's negative, I have negative velocity. So it's constantly decreasing. All right. Now, displacement. Remember when I do it like this, you know, at T0 I move to the right, At T1, I'm at this point. From T1 to T2 seconds, I'm here. And then at T2, I again start moving to the left. And at T3 seconds, I reach this point again to the very start. Now at this point, remember when I drew the curve like this in the distance time graph, we weren't sure if our velocity is going to be positive or negative, but we did know one thing for sure at time time T4, like T3 to T4. And that was that the speed is, increasing constantly. But we didn't know about the velocity because, the distance can be positive. If at this point at, T3, even if I move to the right, my distance is positive, or to the left, my distance is positive, right? But in this case, there is a difference. What is it? Displacement it accounts for direction. So if the displacement is positive, then I know that if, the displacement's, moving up, right? I'm getting positive values if I look at the y-axis, then it has to be moving to the right. Okay. And so in that case, my velocity is positive and it's constantly increasing. But let's say, at T3, I drew the displacement time graph like this. Well, what does this mean? This means that, above the zero, I have positive values of displacement. Below the zero, I have negative values of displacement. Well, this tells me that the displacement is now negative. What does negative mean? It means that now the particle is moving to the left of the origin, which was, this point right here, like all these points at T0 and then T3. So I'm moving to the left right? Because the displacement is negative. And so I know for sure then that it is negative, the velocity is negative, and it's constantly basically decreasing. So that was an important point. Displacement time graphs can become negative, and distance time graphs are always positive. Okay, so let's do this quick question. Figure number 2.1 shows the thinking distance and the braking distance for a car driven at 100 kilometers per hour. The car has old smooth tires. All right, calculate the total stopping distance. Well, we add them up. 21 plus 75 is 96 meters. All right, make sure that you mention meters. All right. All right, the car is now fitted with new tires. At a speed greater than 100 kilometers per hour, the total stopping distance is the same as in A. All right. So think about it. We had old tires, and this braking distance with old tires, and we were traveling at 100 kilometers per hour. That's our speed. But the braking distance was 96. Now we have new tires. All right, but our speed is greater than 100 kilometers per hour. But it says that, the stopping distance is still the same, right? The stopping distance is the same, but the thinking distance and the braking distance is going to change. Now with the old tires, when we replace them with new tires, the friction increased, right? Because they're in much better shape. So now when I apply brakes, right? What's going to happen? So the thinking distance is going to be the same, whether or not I have the old tires or the new tires. Like you're driving the car, you don't care if the tires are old or new. The thinking distance is going to be the same. At the moment you see the accident right here, right? You recognize the accident when you're at this point, and you apply the brakes, right? So when you apply the brakes, you don't apply the brakes. This is where you see the accident, and at 21 meters is when you apply the brakes. So the thinking distance did not, change because of the tires. Because of the tires, it did not change, right? But we see that, in the new tires case, the speed is greater than 100 kilometers per hour. So if the speed is greater, that means that I need more time I'll be taking more time, because speed is distance divided by time, right? So if the speed is greater, then I need more. Then I have less time. My apologies. I'll have less time to react. Basically, if the speed is greater, you have to travel more distance. You'll be traveling more distance. All right. You'll travel a greater distance before applying the brakes, because you're going fast, right? If you're going on the road and you see an accident in front of you, if your speed is greater, right, even if you realized that even if you've realized that there's an accident up ahead, it will take you'll cover a greater distance because your speed is greater, right? Before applying the brakes. So the effect, so we'll say, the effect of increasing speed is basically, in the explanation, the increasing speed decreases the thinking distance. Oh, sorry, my apologies. Increases the thinking distance. I'm just using abbreviations, but you can't do that in an exam. Just letting you know. Anyways, explanation. Basically, speed equals to distance divided by time. And so if I have a greater speed, I'll be traveling a greater distance before I react. State and explain the effect that the increase in speed and the new tires have on the braking distance. All right, that the increase in speed and new tires have on the braking distance. Well, when it comes to braking distance, the new tires, even though I'm traveling at a greater speed, right? Because I have new tires, there's more friction, and so I'm going to stop quicker. All right, so the braking distance is going to decrease. All right, so we can say that it's going to decrease because decrease with new tires. The braking distance will decrease with the new tires, and the explanation, well, friction increases because our new tires are much better, in a much better shape. Okay. So you can see that the thinking distance increased with the greater speed. Let's say it became 30 meters, but the braking distance decreased to, let's say, 96 minus 30, let's say, to keep the stopping distance the same, 66 meters. But the stopping distance is the same. All right, so now we come to acceleration. Remember that in the very beginning when I was talking about velocity, I drew 2 points, A and B. And I said that the only things that I am concerned with, the only things that I do know of are my measurements at point A and point B. So at this point, D1 equals to, let's say, 0, and I have a distance D1 equals to 0. And then point B, I measure the length and I find that, the distance between them is, let's say, 10, and T2 equals 10. All right. And I said that if I know just these two measurements of time and distance at points A and B, I can measure the velocity, right? The speed or the velocity, right? But why do we need acceleration, right? Like, the acceleration is the rate of change of velocity, but why do we need it? Let's say that the same person who walked from A to B, he now walked from B to C, and at point C, I made a measurement. I measured the distance from D1 and I found that that is 20. And I measured the time, and the time was, let's say, 15 seconds. So now if I calculate the velocity between A and B, right, it's going to be 10 minus 0 divided by 10 minus 0, which gives us basically 1 meters per second, right, the velocity or the speed. The reason I'm saying velocity or speed, basically positive velocity or speed, right? Given that to the right is positive velocity. All right. Here's where acceleration comes into play. Then the same guy walks from B to C, and point C I made another measurement, and I calculated the velocity between B and C, and I saw that that was 20 minus 10 divided by 15 minus 10 meters divided by seconds. You should always write down the units to keep account of them. So that is 10 divided by 5, which gives me 2 meters per second. So I see that the velocity has increased, and this is why we define acceleration. That, the acceleration is basically how the velocity is changing. Like, if between a certain point the guy was covering some distance in a given interval, in the very next interval, in the very next distance traveled, what's the velocity, like how is he covering that distance at a greater speed or a less speed, like a lower speed. So that's where acceleration comes into play. And then again, the same thing, instantaneous acceleration, we would just make the measurements that we take come very close to each other to get a more accurate result. So I believe I'll be talking about uniform velocity. All right, let's just talk about it here. So it's the same thing. If you grab the concepts for the gradients and how they're changing, then this is very, very easy. Oh yeah, one more thing that I should mention. The acceleration formula for acceleration would then be the final velocity, how the velocities are changing. So between B and C, let's say it was V, and then between A and B it was U. I'm just using characters this these variables this time, like V and U and letters. So V minus U divided by the time taken. So it's the same thing. It's the T2 minus T1, let's say. So this means that it's the change in V, or I can just write this down as V2 and V1 to avoid the confusion. So it's delta V divided by delta T. So the rate, the change in velocity, the change in time, and this whole thing can be considered or called as the rate of change of velocity. So that's acceleration. But remember that acceleration is also a vector, which means that it has a direction. It can either be positive or negative, right? In this case, the acceleration was positive. Why? Because between A to B, my velocity was 1 meters per second, plus 1 meters per second. Between B to C, my velocity was plus 2 meters per second. And so if I, subtract the two velocity, time doesn't include, like time is, the time subtraction is always going to be positive because T2 is always higher than T1. But V2 minus V1 in this case is positive, and so the acceleration is positive. But let's say, that between A and B, the velocity was 2 meters per second, 2 meters per second, and between B and C, the velocity was 1 meter per second. What happened in this case? Well, you take the final velocity V2 minus the initial velocity, which is 2, again divided by T2 minus T1, which can be any time interval. But in this case, you can see that you get a negative acceleration, right? -1 meters per second squared. This should be meters per second squared. Why? Because time is this guy right here, that's just seconds. But remember, velocity is the rate of change of distance, right? So it's delta D. If I replace velocity by delta D, right, it's delta D divided by delta T times delta T, right? So the bottom becomes S squared. So it's meters per second squared. Okay. So the uniform velocity displacement time graph. So let's say I draw something like this, right? What does this tell me? So this is velocity, or let's say speed, and this is time. So what's happening between, let's call this T1, let's call this T2, T3, and T4. What's happening between T0 and T1? Well, now because I'm the rate of change of velocity is acceleration. That's the gradients. The gradient is the measure of the acceleration, right? The gradient tells us the acceleration. So let's see, and in this case, you're not going to use that visualization technique. Don't use that here. That was just for distance time graphs, right? For velocity and speed, that's not going to work. Okay, so from T0 to T1, I see that I have a positive gradient, right? So from T0 to T1, my acceleration, that's what I'm measuring. From T0 to T1, let's take this to the top acceleration. So from T2 to T1, my acceleration is uniformly increasing, right? It's constantly increasing. All right. What about T1 to T2? Well, from T1 to T2, my acceleration goes to 0. Why? Because see, at this point, the velocity is this much. But throughout this line, the velocity is at a constant value. So if the velocity is not changing, that means that the acceleration has to be 0, right? There's only an acceleration of the velocity. There's a change in velocity. And so this is 0. What about t2 to t3? Well, again, because it's a vector, we're not only looking at the steepness of the slope, but we're also looking at the direction. So it's negative, right? The direction of the gradient. So t2 to t3, it's uniformly decreasing. What about t3 to t4? Well, t3 to t4, it's going to be again, the gradient is positive, so uniformly increasing. All right, let's say I draw, instead of going up, I went down like this. What then? Well, the only thing that I'm looking at is the velocity, is the gradient and the steepness. The gradient is still negative, and so that means that between T3 to T4 in terms of the red line that I drew, it's again uniformly decreasing, because we're only concerned about the gradient, the steepness, and the magnitude, right? That's what we're looking at. But let me just say one thing. In case I went down like this can no longer be a speed time graph. It's going to be a velocity time graph, because speed, again, is a scalar and it can't be negative. All right. Now, how would we, let's say, all right. So basically, there's one thing that we do know of in terms of direction. And what's that? That is that I can't tell the movement by using the same technique as the distance or displacement time graph, but there's something that I can tell about directions. And what is that? So since on the y-axis I have velocity, right? From t0 to t3, the velocity is constant throughout, even though the acceleration is changing, right? So the velocity is changing, but the velocity has positive values. What does that mean? So for example, I was at some point A, right? So this means that at t0, I was moving to the right, considering that right is positive. I'm moving to the right, and I keep moving to the right. I'm slowing down. I'm increasing, and then I'm becoming constant, right? From t1 to t2, I'm just falling. I have the same velocity, and then I decrease. Like the velocity starts to decrease, but then at t3, right? What I do is my velocity starts becoming negative. And so what happens is that I start moving in the opposite direction now. If it were going up, I would keep on moving forward. But if it's going down, that means that, the velocity is becoming negative. And so I've switched directions. Okay. Let's look at a non-uniform velocity displacement time graph. It's the same thing. It's just that instead of having like constant lines, we can have something like this, right? So if this is velocity and this is time, well, we can see that in this given interval, at first the velocity is increasing, like till this point it's increasing. Remember this curve that we talked about, so it's increasing. If I zoom in till from here to, let's say, here, right? And then it's constantly increasing, like the straight line. So this is the increasing part, then it becomes constantly increasing, right? And then it becomes the gradient changes this way. So remember this is, it's increasing, but it's increasing at a decreasing rate. All right, it stops for a second and it starts decreasing. The velocity starts to the acceleration starts to, the acceleration at this point was 0, right? For a brief second it was 0 because the velocity was the same. In a very short time interval, let's say from here to here, a very short time interval, the velocity was the same and it didn't change. So the acceleration is 0, but then the acceleration starts to decrease again. Well, you can see that at first it decreases like this. So remember what this is? The acceleration, basically. So negative acceleration, there's a word for it, and that's called deceleration. All right. So there's increasing deceleration, because, you know, the gradient is negative. Like if you look at the slope is throughout negative, but it's, you know, as we discussed in the gradient section, this is becoming increasingly more negative, right? So it's increasing deceleration. Then from this point to this point, right, it is a curve like this, a straight line, and so it's uniformly decelerating. And then from this point to this point, you know, it's like this. So it's again a negative gradient, but it's becoming, you know, its deceleration is decreasing. It's not increasing, it's decreasing. Decreasing, but it's like it's decelerating slowly. Here it was decelerating faster. Here it was decelerating slowly and fastly. All right. So let's do this question. It says a car approaches a set of traffic lights. The lights change to red at time t equals to 0. Figure number 2.1 shows how the speed of the car changes with time. So we know that, you know, the change in speed with respect to time is going to give us the acceleration. And since, you know, the values lie above the x-axis, so I mean, you can think of this as the velocity as well, if you'd like. But, you know, the speed and velocity time graphs, the gradients are basically, it gives us the acceleration. So it says the car starts to slow down a short time after the lights change to red. All right. Determine the time between the lights changing to red and the car starting to slow down. Well, you can see that the car was traveling at a constant speed, 20, throughout until this point. All right. So at this point right here, the speed started to decrease, right? So determine the time between the lights changing to red and the car starting to slow down. So the time is then this guy right here, which is 1.4 seconds. Each division is 0.2. All right, state what is meant by uniform acceleration. Well, uniform acceleration means that equal changes in velocity in equal time intervals. Or you can say constant changes in velocity in equal time intervals. Both should be fine. All right, part 2. State how figure number 2.1 shows that the deceleration of the car between t equals to 2 seconds and t equals to 7 seconds is uniform. Now, at 1.4 seconds, if the curve was something like this, you know, till 7 seconds, then we know that the deceleration is basically constant, right? It's constantly decelerating. But we see that the graph is like this, and then it's like this, and then it goes to 7 seconds. So you can just look at the steepness, right? So it was more steep here, and then it was less steep here. And so it was, you know, the deceleration was decreasing, all right? Because the slope is decreasing, the steepness is decreasing. So, you know, the steepness is the gradient, so the gradient's decreasing. And since it's a negative gradient, so, you know, that denotes deceleration. Anyways, so it's decelerating from here to here, and then it's decelerating at a slower rate from here to here. So it says, how does figure number 2.1 show that the deceleration of the car between t equals to 2 to t equals to 7 is non-uniform? Well, you say that, you know, that the deceleration basically is not constant throughout. The deceleration changes at t equals to 4 seconds. You can write that down. All right, I'm just gonna become lazy a little bit, but okay. All right, and determine the distance the car travels from the moment the car starts to slow down until it stops. Well, this is something that I haven't mentioned yet. So remember, you know, that v equals to d by t. Well, then distance is just v times t, right? So distance is the product of velocity and time. So what we're doing is that we're going to take the the distance traveled in a speed time graph can be found out by measuring the area under the curve. All right, so we'll divide this area into 3 parts so that we know the areas of these individual parts, and then we can add them up. So this is area 1, 2, and then 3, and then you can do the calculation. It's going to be, so the first rectangle, 20 times 1.4, all right, plus then it's a trapezoid, so half times if I remember the formula, the sum of parallel sides. So the parallel sides are these straight lines, right? These are the parallel sides, and so that's 20 plus 8. All right, and but 20 plus 8 times the height. So the height is going to be this guy right here. So 4 minus 1.4 plus the area of this guy right here. So that's going to be again half times base, which is 7 minus 4, which is 3, times height. Let me actually write that down as 7 minus 4 so that you guys can follow. Right, 7 minus 4 times 8. So whatever value you get, I'm not going to calculate that because I'm too lazy, but that's the value for the distance. And be sure to write down whatever that value is in terms of meters, like it's in meters. Now, a very key thing that you have to realize is that, in this case, since the speed was given in meters per second, right, remember d equals to v times t, since the speed was given in meters per second and the time was also in seconds, the SNS cancels out. But just in case, if they like change the units, for example, if the time was in milliseconds or the speed was in, let's say, not in meters per second, but rather kilometers per second or something like that, then you'll have to change, the units from kilometers per second to like meters per second before you do the calculations. You have to ensure that, the units are, like if it's second on the, like if it's meters per second, then time has to be in seconds. And if it's, meters per milliseconds, then the time also has to be in milliseconds. So you have to ensure that. All right. One more question. So, it shows the speed time graph for an athlete in the race. During the race, the acceleration of the athlete is uniform in the first 2 seconds. State how the graph shows that the acceleration is uniform. Well, again, it's the same answer. It's equal changes in velocity and equal time intervals. All right. Okay. Determine the distance traveled by the athlete in the first 2 seconds. Again, you measure the area under the curve. So it's half times 2 times 9. So it's midway between 10 and 8, so it's 9. All right, so it's 9. And again, make sure that this is the units match. Meters per second times second, so it's in meters. And you have to write down meters. All right, now it asks you to complete this speed time graph for times between 2 seconds and 11 seconds. Okay, so from 2 seconds to 5.5 seconds, the acceleration of the athlete decreases. Okay, but we'll have to read the next line because it can either decrease like once we reach 2 seconds, right? At this point we're at 2 seconds. Now we can either decrease like this or at constantly, or we can decrease like this, right? So we have to read the next part. At 5.5 seconds, the athlete reaches a maximum speed of 12 seconds. Well, remember, when you reach a maximum speed, right, that's the highest point that you can go to. For a very brief second, the speed is just that value, right? And so the acceleration is 0. So at 5.5 seconds, which is the midpoint between 5 and 6, the speed is 12 meters per second. All right, from 5.5 seconds to 8 seconds. So that means, it reaches a maximum of 12 meters per second. So I'm assuming that, he was not constantly decreasing. So we'll draw the curve, like, it starts to, the acceleration starts to decrease and it reaches a maximum. I do it a little bit above. It shouldn't have been that way. All right, something like this. And from 5.5 to 8 seconds, the athlete travels at a speed of 12 meters per second. So till 8 seconds, I'm at a constant speed. I just stay at 12. And then from 8 seconds to 11 seconds, the athlete decelerates, all right, finishing the race at a speed of 10 meters per second. All right, so 11 seconds, I reach a speed of 10, right? And the athlete is decelerating. Now again, deceleration can either be drawn like this because it's a negative gradient, it can also be drawn like this, like this way, right? But this says that it was the deceleration was higher for it was higher first, and then it's like it started to decrease as you moved on. So it was, the deceleration was decreasing at a so basically the deceleration was decreasing. All right, what about this guy right here? Well, the deceleration was increasing as you moved to the right. In this case, the deceleration was decreasing as you move to the right. The deceleration is increasing as you move to the right. And this is the deceleration is constantly decreasing. All right. And so, the athlete decelerates, finishing the race at speed 10 meters per second. So, you can draw it like, like this. I mean, if I were you, I would draw like this. I think if you draw it in the other, like the other two ways are also possible. Like, they shouldn't be cutting down marks because they didn't mention if it's the deceleration is constant or if it's increasing deceleration or decreasing deceleration. They'll have to mention that, and then we'll choose something specific. All right. So with that, we have, I believe we have concluded the chapter. For some reason, I'm not being able to go to slide 19. There we go. Okay. So the learning outcomes: state what is meant by speed and velocity. Check. Recall and use average speed. Check. What is uniform acceleration and use acceleration equals to change in velocity divided by time taken. Check. No, what's non-uniform acceleration? Check. Recall that deceleration is a negative acceleration. Check. Plot and interpret speed time and distance time graphs. Done. Recognize from the shape of a speed time graph when the body is at rest, moving at uniform speed, moving with uniform acceleration, and then moving with a non-uniform acceleration. And calculate the area under a speed time graph to determine the distance traveled for motion with uniform speed or uniform acceleration. Check. Now there are two more outcomes, but I have left those outcomes for the next chapter in dynamics, because I believe and I think I might be very wrong when it comes to other teachers. I think these two outcomes are much, like, they're better to be discussed when we talk about forces and what's the the gravitational constant and everything. And so yeah, with that, we conclude kinematics. Thank you so much for bearing with me this lecture, and I hope it helped. So yeah, I will see you in the next lecture, which will be on dynamics. Have a great rest of your day, a great rest of your week. Enjoy life, stay positive, and yeah. All right, see you soon.